Thank you. Thanks, Gerard, for inviting me. It's a pleasure to be here to honor Egon's memory. And it's a pleasure to see a lot of good old friends after so many years. It's been 20 years since I left academia. I just wanted to start by telling you sort of two anecdotes of Egon, very quick. And you should not take this to make you think that the scientist that Dan quoted by saying "a scientist said" was Egon. No, I know he didn't mean it, but I will. So the first one is when I was doing my summer paper, and we started working on the Lovaas and Shriver procedure that we ended up calling lift and project. I was working with both Gerard and Egon, and we were very excited about what we were doing. And one day, we walk into Egon's office, and Egon says, "I have good news and bad news." And what is that? And he said, "Well, everything you're doing is just disjunctive programming, and all this lifting and projecting and all this kind of stuff is the stuff that I did in my paper. So it's great that we have this connection between Lovaas and Shriver and the work I did on disjunctive programming." And he said, "That's the good news." And I said, "What's the bad news?" "Well, the bad news is it doesn't work. So you might as well throw it to the garbage." And I'm like, "Oh, crap." So that was the beginning. Then the second anecdote is not one that happened to me, but it happened to the guy behind this work, who is Rob Stubbs. When he did his dissertation on disjunctive programming for nonlinear programs, he went to Egon and he said, "Well, this is what I've done." And Egon told him, "This all sounds very good, but I think it's pretty useless. The only thing you can do is find an application where this stuff works. And if you find that application where this stuff works, then that would be okay." So I was talking to Stubbs as we were preparing these materials, and he told me the story. And I said, "Well, I'm glad I hired you because we found the application where all this stuff works." And what you're going to see today is, I feel a little bit weird because in academic conferences, what you try to do is you try to really show the details of how you got to where you got to. But, I work at a company. What we have is a trade secret. And that trade secret has brought us a long way. And so I'm not going to talk about any of the trade secrets, but I'm going to give you some hope that one way or the other, what we have been working on over the last 20 years has somehow filtered through. And we haven't seen it in any papers, but clearly some people now know what we've been doing. So the whole idea is to talk a bit about how to use disjunctive programming in the context of portfolio optimization. And I think the interesting thing about portfolio theory and what people call mean variance optimization or modern portfolio theory, which was developed by Markowitz, is that a lot of the problems that really come out of this basic knowledge have a lot of interesting disjunctions. And those disjunctions, in many cases, come out as simple binary variables that are used to model certain problems, but in other cases, those disjunctions appear completely naturally in the formulation of the problem. So you don't have to go via integer programming to get to those disjunctions. So what I'm going to do today is I'm going to speak mostly about what I would call a simple problem, because that simple problem illustrates quite a lot the difficulties that you have with what we call indicator variables, and how some of these disjunctive programming techniques can significantly overcome those difficulties that you have with indicator variables. And when I was doing my research here, not in this building, but in the crappy one on the other side, and yeah, we really had crappy offices and crappy desks, but thank God for Tepper, who made a lot of his money not by following Markowitz, but by doing a different way of managing money. But I was always, every time I used to get an instance, and that instance of an integer program had indicator variables that were representing some sort of counting of something, we knew it was bad news. We knew it would be very, very difficult to try to model those problems and to get good results. So the simplest problem that you can think of is this problem, which is here, which essentially is called the minimized tracking error problem. So what you have is you have a benchmark or you have an index. Think about it as the S&P 500 index. And the problem that you have is you want to replicate the S&P 500 index. But rather than using 500 names, actually the S&P has 505, but rather than using the 505 names of the S&P, you just want to use fewer names. Now, this is completely an artificial problem, right? I mean, who on earth thought that using 100 names is good? And why don't you just use the 505? And all the reasons for, taking this problem and restricting the number of names come from operational issues of what it takes to actually implement those kinds of portfolios, right? So if you're trying to track the S&P 500 and you use the 500 names, every time that you have cash flows and you need to buy the 500 names, you're incurring movement in the market, the operational aspect becomes complicated, and so traders and portfolio managers don't like to do that, right? They just like to shrink the number of names that they buy, and in part you can show that you can actually do a very, very good job. So what you lose in terms of precision of tracking the benchmark, you gain in terms of efficiency of both the operations and how the whole process works in terms of how you move the market. Now, what is important about this problem, and this is sort of, as I said, a pretty trivial problem. It has a quadratic objective function, and then it has just the simple weighting constraint that says that the sum of all the names that you hold add up to 100%. And then you have these indicator variables y that essentially represent the maximum number of names that you can hold in the portfolio, right? So I mean, it kind of gets simpler than this. You can explain it anywhere, but actually solving this problem is not that trivial. The Q matrix is one where typically we talk about a factor decomposition. So one of the other things that you learn when you develop solvers for specific problems is that you can actually severely exploit the structure of the problem when you're running the solver. So I'll tell you a little bit when we look at the computational experiments. I'll show you a bit of what is it that we gain by solving a specialized problem relative to what a professional optimization company like Cplex or Gurobi or Mosec or Express, what those guys do, that of course spends a lot more time and money than we do in fixing or in improving the underlying solver. So this is the basic problem. And then what happens is there's quite a lot of additional rules that people have which make this problem even more complex from a combinatorial perspective. And as I said before, some of these are actually not, you don't model them as combinatorial problems, you model them as directly disjunctions. So an interesting version of this problem is when you just say, I want to track the S&P 500, but now because I'm an individual that pays taxes, I want to do it in a tax-efficient way. And then what you're trying to do is you're not necessarily going in and out of the names when everybody else goes in and out. You take into account the taxes that you have to pay. And for those of you who follow this, the tax policy in the US has a lot of combinatorial elements to it because there's a lot of if-then-else kinds of rules that you have to follow. So that's essentially some of the terms that make life very, very complex. I would say that how you model these problems makes a huge difference. And this is one area where we have still today a huge competitive advantage relative to our competition. Then you have what I told you before, the number of names, and then you have this other one, which is also bad news from an integer programming perspective, which is threshold limits on assets. So that's also another operational rule that says if you're going to buy something, don't buy just a little piece of it, buy at least a certain amount, right? Because again, operationally speaking, portfolio managers hate to have lots of tiny positions where you're just holding a tiny amount in your portfolio of some name, which really doesn't add much value and adds operational complexity. You can do the same on trading variables. And in this case, you can just limit the number of trades. So you say, I want to change what I have, but I only want to trade 5, 6, 7, 8, 9, or 10 names. And you can also have thresholds on trades. So these are just some. There's lots of other complications that make this problem sort of even harder. But one of the things that you realize that I was always yearning for is you have a wealth of problems here where you can really try to go crazy in terms of your integer programming research to see how well you can do. So this is just a chart of what happens if you try to solve this problem naively, right? And what you have is that when on this axis, on the x-axis, you have the maximum number of names, and on the y-axis, you have the tracking error. So think about the tracking error as a measure of how far you are. And so what you see is obviously that the bound is trivial because you can always track it perfectly, right? I mean, you can always just get lots of tiny positions and then you track it perfectly because, you know, the W equals B, which means you take the weights equal to the benchmark, is a solution, so you get 0. And you know, in terms of the upper bound, you know, these are just, you know, how you get solutions, which you can get pretty reasonable solutions pretty quickly. Now, what you know, really brought me to tears, literally, when we tried disjunctive programming on this problem was the orange, right? That by doing disjunctive programming, we were able to get lower bounds that look very, very close to the upper bounds. Now, of course, you might say, well, you know, how did you get to those upper bounds? And what I'm going to show you next is actually that the linear programming relaxation, well, the quadratic programming relaxation of the disjunctive program already gives you so much information that getting good solutions, it's almost trivial. And that's illustrated by this chart over here. So what this chart says is, you know, just going back to the previous chart, is now what you're trying to do is you're trying to chart your, you know, where your indicator variables are in the relaxation, and you're trying to compare that. Of course, what you're trying to get to is to 0 or 1, right? So there you go. You know, in orange, you have the variables that are between 0 and 0.001, and in light blue, you have the ones that are, you know, almost 1, right? So what you can see from this chart is that you have almost, I think that the number here is for the first column, you have 435, which are already orange, and 33, which are already light blue. So to get to 50, you don't have to do a lot of work. Okay, so those bounds that we get are so strong, and they give us so much information in terms of the starting solution that we're able to get to the optimal solution. I mean, it's not optimal. You see there is a little bit of a bound. But from our perspective, we argue that it's not worth the trouble to go much further, right? So in the root node, we're already able to get very close. Plus, by the way, the heuristic doesn't particularly need to be that sophisticated. So what we did is, you know, as we were trying to convince more and more of our clients, and as the commercial solvers were getting better, I mean, when we started doing this in the year, you know, 2000, we were so much better than any commercial solver that you know, was not even funny. And what happened since the year 2000 until now, just to be open about this, and you know, one of the things I'm going to say is I'm not going to show much formulas, but you can ask me questions if there's something you want to know. You know, that's one of the things that you have to learn about when you work for a company. Certain things you can put in the slide and certain things you can't. But one of the things that is important to keep in mind is that we have not worked much on the underlying solver, on the relaxed problem solver, which is an SOCP. So we have a second order cone programming solver, which is more or less the same solver that we had in the year 2000. And in all that time, of course, anybody, and you know, with the race that's going on between all the commercial players, mostly in the financial industry, Mosek has been the one that had the most traction, but also Cplex and lately Gurobi. You know, those guys have been putting a lot of work on the underlying relaxed problem. So while we have not done much, most of our work is really on the integer programming part, and that already gives you enough of a difference to distinguish yourself. So what we decided to do in 2012 was to write a paper, and this paper is actually available on our website, that compared the state of the art at the time with our solver. And the answers are more or less here, and I'll show you a few charts, and I know I don't want to take too much time on this because the charts are pretty self-explanatory, but if you start comparing with those solvers, what you see is, and by the way, when it says 60, that means the solver was run for 60 seconds, and when it says 10, is the solver was run for 10 seconds, okay? So, and again, it doesn't matter what 60 and 10 are, this was 2012 computers, but what you could see here is that, compared to traditional solvers, which were already doing quite a lot of magic, including lift and project and Montgomery cuts and all kinds of other things, we were still very, very far away. So there's no way that these guys could come anywhere close. So when we were talking to clients, we were saying, look, if you have a simple problem that is just a quadratic problem or a second-order cone problem without any combinatorial issues, you can just go ahead and buy that. But if you have these combinatorial issues, which are critical for operational purposes, then we still have a huge competitive advantage. And what this chart, so this is just for, sort of the simple problem, right? So now obviously there's more complex problems, and we started running experiments, and this is what's in this paper, adding some further rules. And one of the things that we did was also increase the size of the universe. So now we're not running against the S&P 500 anymore. We're running against the Russell 3000, right? So this problem becomes tougher in the context of the Russell 3000 because there's a lot more choices. There's a lot of names that look really like the same. I mean, one of the things, just sorry to add bits and pieces, but this is I think one of the most fascinating part of this business is that one of the things you learn in the stock market is that most stocks really look alike. There's very few things that determine differences between the behavior of most stocks. And that's why factor models work so well. Because most of the behavior, the return behavior and the risk behavior of stocks is driven by very few factors. The idiosyncratic component, which is the component that is company specific, is really tiny, right? So this makes problems worse because when you have these problems and you have 3,000 assets, then there's many assets that look the same, right? So typical problem of IP, or mixed integer programming, which makes it difficult, is you put something over here and then it appears on the other side, right? So we started making it more complicated, and this is, I would say, a pretty realistic problem where you have active asset bounds, which means you cannot hold any security by more than 3% of your portfolio. You have turnover, which means when you go from one portfolio to the next, you cannot change the whole portfolio. You have a to T% that you can change. The number of names is 200, which is a reasonable number of names for a Russell 3000 universe. And then we had threshold constraints and number of trades, right? So there's different setups here, and it says there which constraints we use. And when we tested this against the solver, so this is just containing the number of names constraint. Again, when you see a bar, that means the solver failed in the time. And then if you keep going, and again, this is just, think about it as a movie, you still keep seeing that most solvers are having tremendous trouble even to getting feasibility, and so on and so forth. So let me just come to today, because this was 2012. So what we see today, and again, at some point somebody's going to ask me what CS1 and CS3 is. What you see today is that the solvers in the market, and these are sort of the same problems, and this LS1, LS2, LO1, and LO2, those agree with the categorizations I did before. And LS means whether it's long, short, or long only, right? Long, short means that some of the variables you could actually go negative. And so what you can see now is that CS3, which is a commercial solver, is able to get very similar success ratios that we are able to get with Axioma. And what you see is that CS1 is still lagging behind. There's 2 points before I finish here which are interesting. One is CS3, which is the solver that gets the closest, is not using second-order cones to solve these problems. What we think is going on is that they're actually doing linear approximations, and one of the reasons that they're getting so close is because they're able to iterate very quickly through various heuristics. So as they iterate very quickly through various heuristics, they're able to get solutions that are quite close to our solutions, but their bounds are still pretty bad in comparison. But they're getting much closer because of these approximations. And we know for a fact that they're doing some sort of disjunctive approximations for those problems. What we see in CS1 is that they're still struggling, but that code is actually running a second-order cone problem. So we think that in the context of second-order cones, these heuristics, these pivoting heuristics are, of course, a lot harder to implement. So a lot of these solvers are having tremendous trouble in getting there. So what's the moral of the story? And I'm going to end. Fine, right? 1 minute. So the moral of the story, from my perspective, is, for a long time, I've been studying general integer programming. And, that was where, as you know, the famous lift and project method was developed and all those beautiful results were obtained. But the people that know the structure, the people that have instances coming from clients, the people who are there day to day, really understanding what are the problems that they have to solve, have a huge competitive advantage. And that's what we have. Ultimately, we're not going to be able to get anywhere close to the sophistication of a MOSEC or a Cplex or a Gurobi or an Express when it comes to the underlying solvers, but still exploiting the structure is able to give us tremendous information. But what is interesting here, what I always thought, is that that exploitation of the structure was going to allow us to get tremendously good solutions very quickly. The interesting thing about this work is that the way we got there was by getting phenomenal bounds. So it is really the underpinnings of disjunctive programming that allowed us to really get to good solutions. Trust me, our heuristics are not by any means sophisticated. It's just that getting such a strong relaxation gives you so much information that you're so close to the answer that way you can actually significantly reduce that gap. Thank you very much. No, it's, we're generating disjunctive cuts. And we're generating disjunctive cuts from the nonlinear programming problem. So, and it's all there. For anybody that wants to see it, it's there. We just don't publish it, but it's there. It's not that we have something that, what we have is, of course, computational results and tricks in terms of how we implement, but all the basics of what we've done are in the literature. It's just that, being smart about how you exploit that literature in the context of these kinds of problems gives you a huge competitive advantage. And we did this, well, I used the royal we, sorry about that, but I didn't do any work on this, okay? I'm just telling you the story. The only thing I did is just hire the people that did the work, which I'll take credit for that one.
What were CS1 and 2?
Sorry, so CS1 is MOSEC, CS2 is Cplex, no. Yes, CS2 is Cplex, and CS3 is Gurobi.
Right, thanks again, Sebastian. Thank you.